Welcome to the solutions to the Regents Physics Work, Power, and Energy problem set, problems number 24 through 26. We'll start with 24, a 14,700 Newton car, that would be the car's weight, is traveling 25 meters per second. That would be its initial velocity. The brakes are suddenly applied and the car slides to a stop. That would be its final velocity, which is 0. The braking force, the average braking force between the tires and the road is 7.10 times 10 to the third newtons. And that would be a force value, F. And because it's a braking force, it would be negative because it's in the opposite direction of the motion of the vehicle. How far will the car slide, that's D, once the brakes are applied? All right, because we have force and they're asking us for displacement or distance traveled, that's a dead giveaway that we're going to use the work energy theorem here. So we start with the work energy theorem statement, W equals delta ET. And we now consider what forms of mechanical energy are being changed in this problem. Well, clearly the car's velocity is changing, so there's a change in kinetic. The car is not changing a height in a gravitational field, not attached to a spring. So the only change in mechanical energy is the kinetic energy. On our next line, we write our formula for work, which is F times D, and we write our change in kinetic energy expression, which would be 1/2 mvf squared minus 1/2 mvi squared, that being the final kinetic minus the initial kinetic. We then go ahead and substitute, and again, our F value is negative, so we substitute 7.10 times 10 to the third newtons times D. Our final velocity is 0, so our final kinetic term is all 0, minus 1/2. And we get to M, and we discover that we don't know the mass of the car, but we do know its weight. So we go over here to the side, and we do a quick little side W equals mg calculation. And we have its weight of 14,700 newtons equals m times little g, which is 9.81. And we find the mass of the car to be 1,498.5 kilograms. And that's what we bring over and substitute for the mass in our kinetic energy equation over on the right. We then multiply by its initial speed, which was 25.0 meters per second. And we remember to square that. We solve for D, and we get 66.0 meters. Note that if you had forgotten to assign the force a negative value, that you would have ended up with a negative distance value, which doesn't make sense, meaning the car went backwards in order to stop. All right, we move on to 25. A hallway display of energy is constructed in which several people pull on a rope that lifts a block 1 meter. The display indicates that 1.00 joules of work is done. What is the mass of the block? I'm going to show you there are two ways to do this problem, and I'm going to show you both ways here. And both are correct physics. And the first one, we're going to just do a work calculation. It told us that 1 joule of work is done. The force that needs to be applied is to overcome the block's weight. So F is mg times D. And then that m value is what we're looking for. 9.81 meters per second squared is the little g value, and the distance it travels is 1.00 meters. With this calculation, we get m to be 0.102 kilograms. The other way to do it is a work energy theorem solution. So we start with our work energy theorem statement, W equals delta ET. We then take ourselves through the various forms of mechanical energy and whether or not they're changing. This block is at rest at the beginning and then it is at rest at the end, so there's no change in velocity, therefore no change in kinetic. It does change a height in a gravitational field, and it's not attached to a spring, so the only mechanical energy that's changing in this problem is gravitational potential energy, so we we say delta PEG. W equals final gravitational potential mgHf minus initial gravitational potential mgHi. We're told that 1 joule of work is done. M is what we're looking for, 9.81 meters per second squared, the little g value. Final height is 1 meter. The initial height is 0, making the initial gravitational potential energy 0 altogether. Again, solve for M, and you can see the similarity between these two solutions, 0.102 kilograms. All right, we finished with 26. A physics book of known mass is dropped 4.50 meters. What speed does the book have at the moment of impact with the ground? Anytime we have a question like this, it's going to be a dead giveaway that it's conservation of energy is what we're going to use to solve it. The other clue here is that the mass is unknown. And what that means to us is that if we don't know the mass, that it's likely to cancel in our calculation, which is also kind of a clue that we're going to use conservation of mechanical energy. So we start with our mechanical energy, conservation of mechanical energy statement, EI equals EF. We then consider in the initial state, before it's dropped, the book is at a height in a gravitational field. It's not moving, so the only initial mechanical energy is gravitational potential. In its final state, at the moment of impact, it doesn't have any height in a gravitational field, so it would be no gravitational potential energy, and it's moving, so it would have kinetic. So our EI equals EF becomes mgHi equals 1/2 mvf squared. There's a mass, an m value in both terms, so that allows it to cancel. Thankfully, because we don't know it in the problem to begin with. We then substitute 9.81 meters per second squared for little g. The initial height, 4.50 meters, and 1/2 vf squared. We solve algebraically for vf, and we get a 9.40 meter per second value to 3 sig figs. All right, more practice with these work, energy, and conservation of energy problems as we do numbers 27 and 28 in class tomorrow.